Thank you. So this is the last of a series of presentations on the Go to Southeast Water Balance project. What I will do for my part is present the conceptual framework that we have used to characterize groundwater surface water interactions. Before I get to that, let's have a look at a brief history of the different types of groundwater surface water interaction studies that we've had in Australia in the last few decades. In the 1970s and 80s, the big topic was dryland salinity. What happens when you remove native vegetation from the landscape in semi-arid regions, increase recharge rates, and change the extent of shallow water table in the landscape. So the legacy of this work is still with us today through initiatives such as the Murray-Darling Basin Salinity Strategy. Then in the 1990s, a new buzzword happened, groundwater-dependent ecosystems. And that led to a lot of work cataloging where these ecosystems were, and we're still in the process of trying to include them in water management plans. And we heard a beautiful example of this morning in one of the plenary sessions. Now, come to the 2000s, during the drought, conjunctive water use was the buzzword. We're dealing with a problem where in some cases, especially in alluvial aquifers, where sometimes we gave the water away twice, once as surface, once as groundwater. And the new policy initiative said that we must quantify the exchanges between groundwater and surface water so that we don't have this double accounting. And this is very much part of recent initiatives such as the Murray-Darling Basin Plan. Now, my proposition for you today is that during this period, from the 1970s to the present, the scale at which we have approached the problem of groundwater surface water interaction has shrunk. In the days of dryland salinity, it was big picture, regional scale. For conjunctive water use, we're often at the scale of river reaches. Now, if we look at the kind of problems that we're looking at now, the impact of large-scale groundwater pumping for extraction of coal seam gas, or looking at the impact of climate and land use change on water resources, my proposition for you today is we should make an effort to move away from looking at the local scale and perhaps use some of the lessons that were learned in the early days of dryland salinity when the emphasis was regional. So I've been through this, so I'll just present the conceptual framework for the development of the groundwater surface water interaction model for wetlands in the southeast. We've come up with 5 factors that should be considered when doing this. The first one is position of the wetland in the landscape. To illustrate some of the examples, I'll use some of the numbers some of the characteristics of 3 study wetlands that we looked at during the project. They're among the 13 priority wetlands that are being monitored by the state government in the southeast, and they include Deadman Swamp, Bull Lagoon, and also Lake Road near the coastline. So let's look at the landscape here. And what we have is 3 wetlands in different positions. And typically when looking at a regional hydrogeological system, it's typical to classify flow paths into local systems, which would have residence times of years typically, intermediate scale system, which would have residence times of decades or longer, and also the regional one, the one that have transit times in the centuries to millennia. When looking at this, in particular at the regional scale, you can then start to assess where the wetlands fit in this system. So you'll have wetlands that will be located in regional recharge areas, in regional flow-through and regional discharge areas. And right away by knowing this, you can say something about how groundwater surface water interaction will operate in these different wetlands. Typically, for example, if you look at wetlands in regional recharge areas, they're the ones that have the most variable water tables on an annual basis, and they will often be the first one to dry during droughts. And this is a cartoon, but it represents water table variations in Deadman Swamp, which are typically 1 meter or more per year, and Deadman Swamp is a wetland that is currently quite dry in this landscape. At the other end of the spectrum, if we look at Lake Robe along the coastline, the water table variations are centimeters to tens of centimeters per year, and overall fairly constant. Because we're in a semi-arid landscape, we can also say something about the salinity of the regime of the wetlands by their position. So typically, in places like Deadman Swamp, it used to be fresh water, but it hardly any water in it anymore. But the groundwater surrounding wetland is quite fresh, 1.5 to 2 millisiemens per centimeter. If we look at Bull Lagoon, in what we think is a regional flow-through zone, the wetland itself varies in salinity between fresh and brackish, and the groundwater underneath the wetland is fresh to moderately brackish. At the coastline, Lake Robe, lustily saline. Last year, the Lake Robe was twice seawater in salinity, and the groundwater near Lake Robe is about half seawater in salinity. The position in the landscape, the effect of position in the landscape will also be influenced by topography. This is one of the first studies using computer models to look at groundwater flow systems, and it's a pretty simple example. We have a landscape that has a low gradient, but in one case on top, the topography is flat. In the example below, there's hummocks and hollows. So right away, you can see that just by adding a little bit of variation in the topography, you create, if you look at the example below, a multitude of local and intermediate scale flow systems, whereas in the example above, the main flow occurs through regional flow paths. So landscape position, first factor. Second factor is subsurface control. Again, this is a cross-section of our landscape, and here what we have is a bedrock because of a fracture of some other geological process that comes back closer to the surface. That's one form of subsurface control. We also have next to the coastline the salt wedge. The net effect in both cases will be to induce the discharge of groundwater further inland that you would expect otherwise. Now, if we look at geological cross-sections of the lower southeast, here we have two examples. They are at the same scale. In the north, orange is bedrock, and the other colors represent different aquifers and aquitines. So you can see right away there's quite a bit of difference between the northern and southern part of the study area. In the north, the aquifers are thinner, and there's some evidence for bedrock control at intermediate distances, whereas in the south, the aquifers are thicker and remain fairly constant in depth all the way to the coastline. So just by looking at this, you would have the feeling that there will be more likely to have bedrock control in the north, less so in the south. Now you keep this square in mind. I'll get back to it in a second. Now, in nearby areas in the Eastern Murray Basin, these bedrock regions with regional discharge areas induced by bedrock control actually are quite prominent, and they actually can shape the whole landscape. Phil Macomber came up with the concept of whole landscapes shaped by regional groundwater discharge, and he gave them the name of Boinkas, after the name of a small locality where he first observed the phenomenon. And this is the example of the Rock Plains, Boinka in western Victoria. Now, my proposition today for you today is that we may have our own Boinka system in the southeast region. This is the Bull Lagoon region. And you may remember this red square on the previous slide where we had a major fault creating bedrock coming up. That's exactly where Bull Lagoon is located. So I'm suggesting that this multitude of shallow wetlands, including Bull Lagoon and others, is a regional groundwater discharge feature. Now, unfortunately, the term Boinka isn't quite caught on because there's another definition for a Boinka. I was going to tell you what it is, but the organizers of the conferences explicitly forbidden me to do so. So you probably will have to Google it. The three other factors that we are considering in modeling groundwater surface water interactions in the Southeast are more local in extent. They include local geological features like the presence of a clogging layer, the potential to supplement wetlands with surface water, and also the morphometry of the wetland. I'll go through this very quickly. Clogging layer is simply any geological medium that has a lower hydraulic conductivity than the surrounding aquifer. And the significance of them is to induce, as you can see on top, perch water table conditions where the wetland or the stream is still full with water even when the water table is below the wetland. Now, there's still exchange of water between the two through an unsaturated zone. But the difference is that you need a clogging layer for this to happen. Without a clogging layer, the wetland simply dries when the water table drops below. Now, you don't need extensive geological medium to create a clogging layer. In many places in the Murray-Darling Basin, half a meter of clay over sand is enough to create perch conditions in the rivers. In the Southeast, it's probably even more complicated than that. Below you have a geological cross-section in the vicinity of Bull Lagoon, and you can see clay layers, marl, a range of features. So unfortunately, that's one of the challenges that we have when looking at groundwater surface water interactions for individual wetlands, is that each wetland will have its own little geological environment which will determine exactly how it will respond to change. The other complication when dealing with the Southeast is that some wetlands do and some don't really receive surface water inputs. Now, to create models that fully couple surface runoff from a catchment with a regional groundwater model is very, very difficult. However, we probably have a break in the Southeast in that there's a clear pattern in the way water is delivered to the wetland. What this graph shows is the hydraulic head stage in Mosquito Creek, the inflow to Bull Lagoon. And there you can see that when there is runoff into the wetland, it typically happens at the end of winter, early spring. It's fairly brief. So as a first approximation, the way we can include this surface runoff into wetlands is to simply assume that every year at the end of spring, we top them up with a little bit of water. And finally, a key feature for wetlands is their morphometry. And the type of wetland that we're focusing on are the deflation basins. The sort of wetlands that you see in places like Bull Lagoon are fairly shallow, small, and semi-circular. And the key challenge there is that they're so shallow. Very small differences in their morphometry can make a significant difference in their water regime. For example, if you look at Bull Lagoon, it's an intermittent wetland. It's not always full with water, whereas just north of it, Little Bull Lagoon is a permanent water body. And the only difference between the two is that Little Bull Lagoon is 1 meter deeper. And that's all you need to make a significant difference in their hydro period. So that was a long introduction for what actually is going to be the groundwater surface water interaction model for these wetlands. When we started this, we had in mind fairly complicated scheme that would try to represent in detail things like clogging layers, but I think we turned around and decided that probably more important to try to capture the influence of the regional processes first. So the wetland model itself is going to be very simple, a two-dimensional mudflow model with the potential to have different types of wetlands in depth, presence of a clogging layer, and so on. Now, I won't go through the details today, but a very simple tool. So in conclusion, I hope I've convinced you that wetlands are part of hydrogeological systems, and these are made up of regional, intermediate, and local scale flow paths. It's important to understand where wetlands fit in such hydrogeological framework because it influences a lot the time scales at which they will respond to change. If your wetland is part of a local system, it could respond at the scale of years to months. If it's part of a regional system, it can take a long, long time. The tertiary limestone aquifer is still adjusting to changes to land use in that have occurred since European settlement. And often when people model such systems, they start as far away as the last glacial age to include past variations in the water table. So understanding where wetland fits in this system is very important to customize how we approach modeling change. And finally, I think there is, especially in the early stages, there's a real benefit to try to come back up, try to look at groundwater surface water interaction in these wetlands at the landscape perspective rather than a focus on single wetlands. Thank you.